A body of mass m is projected vertically from the ground with initial velocity u. It experiences a resistance force with magnitude mk v to the power 4, where k is a positive constant, and a gravitational acceleration g. Let its velocity at some time t be v, and also let its vertical displacement from the ground be x. The first part, prove that x equals this expression here. Alright, so for part I, what do we have? We have a particle being projected vertically from the ground. We were told that it initially has some velocity, so our v is equal to u, and we can define this as the origin. So the ground is the origin, and we should say that this is the positive direction of motion. What else do we have? We have a resistance force with magnitude mkv squared. So the resistance acts in the opposite direction to the direction of positive motion, and that's mk v, sorry, not squared, v to the 4. And we have our force of gravity acting down, so mg. Okay, so my sum of forces should be equal to mass times acceleration. Now, our sum of forces is going to be, both of them are negative because they're in the opposite direction to the direction of positive motion. So it's negative into mg plus mkv squared. V to the 4, I keep saying squared. V to the 4 is equal to mass times acceleration, and I can cancel my masses. So take a factor of m out there and cancel it with this m here. Okay, now what does the question want? It wants x in terms of v. So my expression for acceleration is going to be v dv dx. And that's going to be equal to negative of g plus kv to the 4. Okay, so if I do a bit of rearranging, I will get dx on this side, and on this side I'll have negative v over g plus kv to the 4 dv. And now I want to integrate both sides. So I integrate, and what do I get? Well, here I get simply x, and here I have an integral, but it's not really in any standard form as we can see it so far. So if I look back at my question, I can see that my x is going to be equal to some sort of a tan inverse. So I'm expecting to have something of the form, or something close to the form of 1 plus a squared plus x squared when I'm integrating. I'm expecting something of that kind of form. So what I should do, let me just write this integral once more. G plus k v to the 4 dv. I'm going to let's pick a variable, maybe w equal to v squared. And the reason I've done this is because now, if I was just to substitute my w in the denominator, I have some constant plus omega squared, or w squared. Let's just say w squared. So if I use this substitution, I have to differentiate it, and now I can substitute in. So negative v, well, what's v? No, we're going to use this v dv here, and that's going to be dw on 2 v dv. Yep, that's better. So I have a half, and there's the minus there. Now the v dv is going to be the dw times a half, divided by g plus kw squared. Let's move this out of the way. G plus kw squared. All right. Now let's just divide the top and the bottom by k. And I will get negative 1 on 2k over g on k plus omega squared dw, and that's my integral. All right. Now I have a standard form of the tan inverse. So it's going to be this, which is a constant, taking it out. Then it's going to be 1 on a. Now what is a? A is the square root of g on k. So 1 on a is going to be the square root of k on g. K on g. Tan inverse of omega, or w, I keep saying omega, but really let's just say w, divided by a, which is g on k, and I have a constant. I can do a little bit of simplification here, and I'll get -1 divided by 2 the square root of kg, tan inverse. Now, omega, or w, is equal to v squared, so that's v squared. And here I have the square root of k on g in the denominator, which is really just k. Sorry, the square root of g on k in the denominator, which is really k on g, the square root of k on g, plus c. Now I'm going to use my initial conditions to work out what my constant is. So, when t is equal to 0, x is 0, and v is u. So if I was to sub that in here, that would give me that c is equal to 1 over 2 times the square root of kg, tan inverse the square root of k on g, u squared. Alright, so therefore, what's my x? My x is -1 on 2 root kg, tan inverse of the square root of k on g, v squared, plus my constant, 1 on 2 root kg, tan inverse the square root of k on g, u squared. And in the question, we were also told that we may assume without proof that tan inverse of a minus the tan inverse of b equals the tan inverse of a minus b on 1 plus ab. So we're going to use that. We're first going to factor out 1 on 2 root kg. So 1 on 2 root kg. And then I'll be left with tan inverse of something minus the tan inverse of something. And I can go ahead and use that formula that I was given without having to prove in the question. So that will result in tan inverse of this, which is like our a, k on g u squared minus k on g v squared divided by 1 plus the multiplication of these two. So when I multiply this by this, the square roots will go, and I'll be left with k on g times v squared u squared. And then just tidying it up, I can multiply everything by g, the top and the bottom by g, so I'll be left with this. Tan inverse, if I multiply everything by g, that'll become the square root of kg, and for both terms I can factor that out, and I'll have the square root of kg into u squared minus v squared, divided by multiplying the denominator by g, that becomes g plus k v squared u squared, which is what we were asked to show. Part 2. Prove that the maximum height is h equal to 1 over 2 root kg tan inverse of u squared times the square root of k on g. Alright, so let's just write down the result that we had from the previous part, which was that x equals 1 over 2 root kg tan inverse of the square root of kg u squared minus v squared divided by g plus k u squared v squared. Alright, now the maximum height. At the maximum height, we always know that the velocity is going to be 0. So capital V equals 0. So therefore x equals h, because now it's at its maximum height, and that's equal to 1 on 2 root kg. Subbing in v equal to 0, I'm left with, here I get kg, times u squared minus 0, so just u squared, divided by g plus, this term is going to go to 0 because v is 0, so that is just going to be g. And so I'll have 1 on 2 root kg, tan inverse, square root of kg divided by g is the square root of k on g, u squared. And I've proven what I needed to prove. And the final part asks us to find the limiting height as capital U goes to infinity. So as we increase our initial velocity indefinitely, what is the limiting height? What is the limiting maximum height? So as u goes to infinity, h is going to be equal to the limit, as u goes to infinity, of 1 on 2 root kg tan inverse of the square root of k on g u squared. Now this is just a constant, so I can take it out, square root of 2 kg. And I'm taking the limit as u goes to infinity of tan inverse the square root of k on g u squared. So what is this limit? Well, if we have a look at the inverse tan graph, let's draw it over here, as u is going to infinity. So if u is going to infinity, then clearly u squared will go to infinity, and this whole term will go to infinity. So the argument of the function, that is the number inside here, is going to infinity. If this is pi on 2, this is minus pi on 2. This is what our inverse tan looks like, something like that. So my argument, or whatever's inside my function, is going to infinity. That means this is going off to infinity, and it's approaching pi on 2. So the limit of tan inverse as the argument goes to infinity is equal to pi on 2. So this is 2 root kg times pi on 2. And so therefore, I can write that h equals pi on 4 square root of kg as u goes to infinity. And that is the end of the question.